This recording is for Math 241, Mathematics for the Elementary Teacher, and this is day 3, where we will discuss in this video the essence of number theory and the study of how whole numbers work and their relationships with one another. So if we look at this example here, we look at divisibility properties. So you see this format, this A and this line and then B, and that just means does A divide B? So if A divides B and A divides C, then A should divide B plus C. So let's give an example to that. And I do have examples written over here, but I want to talk through those. So let's say that 2 divides 6. So you ask yourself that. Does 2 divide 6? The answer is yes, and it results in 3. And you would ask, well, does 2 divide 4? Yes, the result is 2. So therefore, it's your symbol for therefore, shorthand, therefore 2 divides 6 plus 4. Because then what is 6 plus 4? Well, 6 plus 4 is 10. So 2 would divide 10 because 2 divided 6 and 2 divided 4. So let's look at another example. Will 3 divide 15? Will 3 divide 18? 3 divides 15, yes, the result is 5. 3 divides 18, yes, the result is 6. So therefore, 3 will divide 15 plus 18. And we think about it, what is 15 plus 18? Well, that's 33. Will 3 divide 33? Yes, it's 11 times. Notice what your factors 5 and 6 will sum to be. It'll sum to be 11. Back to the first one. 6 plus 4 is 10. 2 will divide 10, and the result is 5. We'll look at your factors here. 2 plus 3, they would equal 5. So let's look at one more. Will 4 divide 12? And will 4 divide 18? Well, will 4 divide 12? Yes, 3 times. Will 4 divide 18? No. So therefore, 4 will not divide 12 plus 18. And if we think about that, that's my eraser here. That is 4 divides 30. That would be the question. And it does not divide 30. So what you're looking at is some examples of your divisibility properties. And the notation, that's a little different than what you've seen it, but that is a very common standard notation in mathematics to show, well, will this divide this? And so we have situations where we're looking at if it divides one number, yes, and divides another number, yes, then it should divide the sum. So let's look at the next page where we're talking about factors and multiples. Okay? Factors and multiples are two items that are confused quite a bit. Students really, think about the classroom, students do get these mixed up quite often. For instance, you take the number 12 and 7. Well, 12 times 7, or 12.7, or 12 with parentheses around 7, they all are implying multiplication. And you get 84 as a result. Well, that just means that 12 and 7 are both factors. And 84 is what we call the product. So if you look at the formal definition here, it says if A and B are whole numbers, A is 12, B is 7, and A is not equal to 0, and 12 is not equal to 0, then A is a factor of B if and only if there is a whole number C. So A times C is equal to B. And it says that if A is a factor of 84, then there is a whole number C that can multiply by A to give you B. So 12 is represented as A up here, 7 is represented as C, and 84 is represented as B. And so you're looking at this equation right there. So therefore, we could write it in this formula when A divides B. Another example here with 24 equals 8 times 3. So we know that 8 and 3 are both factors of 24. And then notice the notation here. Will 8 divide 24? Yes. Will 3 divide 24? Yes. So that moves us into different types of divisibility tests. So we are going to look at these values here, but we're going to look at just a lot of different situations so we can kind of make I know we can put numbers and divide with calculators, I understand that, but this whole idea here with students is for them to get an understanding of looking at patterns and to see if I have to divide something, how do I know what factors I could choose or a factor that I could choose? And so think about divisibility test for 2, okay? So let's think about numbers that are divisible by 2. Well, 2, of course, is divisible by itself. Think of another number, 4. 2 will divide 4. 2 will divide 6. 2 will not divide 3. 2 will not divide 5, of course, evenly. 2 will not divide 7 evenly. 2 will divide 8 evenly. 2 will not divide 9 evenly. 2 will divide 10. And then 2 will not divide 11. But then when I get to 12, you'll notice it divides 12, it divides 14, it divides 16, it divides 18, it divides 20. You start looking at these patterns and you notice, well, if the number ends in a 2 or a 4 or a 6 or an 8 or a 0, then 2 will actually divide that number. So all numbers that end in 0, 2, 4, 6, 8 are divisible by 2. So let's think about 3. Think about, and we can look at some of the lists up here. What numbers are divisible by 3? Well, we can add some more in here because 3 is divisible by 3, not 2, not 4. 6 is divisible by 3, not 5, not 7, not 8. 9, it does divide 9. It doesn't divide 10. It does divide 12. It doesn't divide 11 or 13 or 14. So it does divide 12. Doesn't divide 16. It does divide 18. It doesn't divide 20 or 22. It does divide 24. And notice what we're looking here is it's 3 times 1. 3 times 2 is 9, or 6. I didn't put 6 there. 3 times 3 is 9. 3 times 4 is 12. I didn't write 15 in there. 3 times 6 is 18. 3 times 7, I didn't write 21, 24, 27, and so forth. So an interesting way to know if 3 will divide a number is to look at, for one, you can look at the single digit numbers and notice that 3, 6, and 9, those three will divide. But notice the rest of them, 12, 15, 18, 21, 24, 27. If you think about the sum, so if the sum of the digits, the sum of the digits is divisible by 3, then 3 will divide that number. So if you look at 12, what's 1 plus 2? 3. So 3 will divide 3. What's 1 plus 5? 6. Well, 1 divides 6. And so forth. So like take 21. Well, that's 2 plus 1, and we're back to 3. And 3 will divide 3. And then we've got 4. We'll look at that one. And if we see 4 will not divide 6, it will divide 8. 4 will divide 12. So, and 16, and 24, and all these numbers. So what we're looking at for numbers that will divide by 4 is we're looking at the last 2 digits, okay? And in this case, we have 8, and so we can look at it as 0, 8, or 0, 4, or then we got 12, and then we got 16. So it does divide these last 2 digits. But if we went to a larger number, like 116, would 4 divide 116? And yes, if you look at the last 2 digits, and I'll clean that number up a little bit. If you look at the last 2 digits there, 116, it's not any better, is it? 4 will divide that number. Let's look at 5. 5 and 10 really go together in this case. Because if you think about numbers that are divisible by 5, well, we've got 5, we've got 10, 15, 20. We're thinking about all these numbers that 5 will divide. And if you notice a pattern, the pattern is in the ones place. So we're looking at the last digit, so we're looking at the last digit with 5. If a 5 or 0, if a 5 or a 0, then we know that it would be divisible by 5. And then we can look at the same with the last digit. If it ends in 0, again, it's the last digit, and if it ends in 0, then we know that it's divisible by 10. So then we've looked at 2, we've looked at 3, 4, 5, 10. 8 is similar to 4, and we're thinking about the last 3 digits. And so if I had 188, 8 would divide 188 because it divides the last, that's going back to 4. If 888, we know 8 would divide 888 because it divides the last 3 digits. We know it divides 800 because it also divides the last 3 digits. So then we also have 6 and 9 to look at. 6 is interesting because if the number divides, if you think about, will 6 divide it, okay? Well, think of all the numbers that 6 will divide. It'll divide 6, it'll divide 12, it will divide 18, it will divide 24, okay? It'll divide 30. So if you think about 6, if 2, because notice 2, 4, 6, 8, 0, if 2 and look at the sum of 1 and 2 is 3, 1 and 8 is 9, 2 and 4, 6, 3 and 0, 3. The sum of the digits, remember, are divisible by 3. So if 2 and 3 divide 6, then we know 6 will divide it. And then 9 is very similar to 3, and it's back to the sum. So if the sum of the digits is divisible by 9, then we know it's divisible. Next, let's look at prime and composite numbers. So I want you to think about factors, okay? We talked about factors earlier, and we think about the factors of 1. Well, the only factors are 1, so it's only 1 for the number 1. And so we would say the number of factors, well, that would be 1. The number 2, well, what are the factors? Well, we've got 1 times 2 gives us 2, so we would say the number of factors would be 2. What about 3? We've got 1 times 3, so it also has 2 factors. 4, we have 1 times 4, and 2 times 2. Well, 2 repeats itself, so really we have 3 factors, 1, 2, and 4. 5, we have 1 times 5, so we have 2 factors. 6, we have 1 times 6, and 2 times 3. So this one, we actually have 4 factors. 7, we have 1 times 7, so we have 2 factors. 8, we have 1 times 8 and 2 times 4, so we have 4 factors there. 9, we have 1 times 9, we have 3 times 3, so we actually have 3 factors here. 10, 1 times 10, 2 times 5, we've got 4 factors. 15, we've got 1 times 15, 3 times 5, we've got 4 factors here. 20, 1 times 20, 2 times 10, 5 times 4. So what do we got? 2, 4. We've got 6 factors. 23, we only have 1 and 23, so we're back to 2 factors here. 36, we've got 1 and 36. We've got 2 and 18. We've got 3 and 12. 4 and 9, 6 and 6, and then we start over again. So it looks like we got 10 factors here. And then 45, 61, 98, we just continue on and on. So we're looking at some patterns here to determine if something is prime or composite. So if you look at, if we look at this one, we only have 1 factor here. And then we have factor 2, 2, 2, 2. Any others that just have 2 factors down here? These only have factors of 2. So if we look at the number 2, 3, 5, 7, just the ones we listed, and 23, we would call these prime. Okay? Because we only have two factors. And then we've got 3, 4, 4, and 3, and 4, and 4, and 6. And then we got all the way down to 10. So anything that was not in blue circled, so 3, 4, and above, we would call composite. And then that leaves us with this one right here. 1 is neither prime or composite. So again, if it's a prime number, we're only looking at two factors. If it's a composite number, we know we have 3 or more factors. And what did we say about 1? 1 is just, well, it's odd. It's a neither, because it's neither prime nor composite. Next, we're looking at prime factorizations. And we got composite numbers can always be written as a product of primes. So, prime factorization, we're thinking about factor trees. Okay, so let's take a few examples. So I do have 30 here, so let's look at 40. So when I factor 40, all I'm thinking about is just what are the first two factors that come to mind. And now you can start to think, especially when you're looking at factors, well, where do I start? Well, think back on your divisibility rules. So notice this ends in 0. So that's a great place to start, would be 10, or maybe you saw 0 and thought of 5. Okay, so 5 and 8 or 10 and 4. Doesn't matter where you start. You could have used 2 and 20. But once you get two factors, you want to try to factor again. Your goal is to get to a point to where you have only primes. And 2 is prime and 5 is prime based on our numbers that we looked at. And so I would ask you to write this in exponential form. So how many 2's are being multiplied together? That would be 3. So we'd write 2 to the third because there's 1, 2, 3. And then we have 5 to the first. So this is what I would want to see. 2 to the third times 5 represents 40. Now look at here. Here's a 5. We know a 5 is part of it. And 8 is actually 2 times 2 times 2 times 2 times 2. And so we could rewrite this as 2 to the third times 5, which is the same as what we had. So notice we wrote it in the order. I wrote it in the order with the smallest prime first. Let's try another one. Let's look at, let's say 48. Okay, so if we look at 48 and think about factors, well, 4 plus 8 is 12. So I know that 3 would divide 48. And I can look at the last two factors and I know that 4 will divide 48. So I could say 4 and 12. 4 will factor to 2 times 2. 12 would factor to 2 times 6. So I'm just going to continue to write these down. And 6 factors into 2 times 3. So how many 2's am I dealing with? 1, 2, 3, 4. That'd be 2 to the fourth times 3. So every composite number can be written as a product of primes. And so what if I had 888? Okay. Well, as I said earlier, I know 8 will divide because it'll divide all 3. And so this one would be 111 times 8. and then 8 would be 2 times 2 times 2, and 111 would be 3 times 37, and 37 is actually prime, so we would say 2 to the third times 3 times 37 would give us the prime factorization of 888. So on homework, I would ask you to, any given number, just want you to show me the prime factorization using that factor tree model to where you get it down to all primes, and then I would like for you to write it in your using your exponents. Greatest common factor, okay? And we're going to look at this using the same thing as exponents as well. And notice that I have here, we're going to look at grouping our bases and exponents, and then we're going to find the highest amount in common, okay? So let's say we'll take 20 and 45. So if we go ahead and factor, so I know 4 times 5, 2 times 2 times 5, so I know it's 2 to the second times 5. And then we'll take 45 and we'll say, well, that's going to be 9 and 5, of course, because it ends in 5. So I know 5 divides it. And then this would be 3 times 3 times 5. So this would be 3 to the second times 5. All right, well, you're looking for the highest amount in common. So when we're talking about the GCF, we would say, well, this one all has 2 to the second, but this one doesn't even have a 2 as a factor. Well, this one has 3 to the second. Well, this one doesn't have a 3 as a factor, but they do have a 5 in common, and only one 5. So the greatest common factor of 20 and 45 would be 5. So let's look at one more. Let's say 28 and 36. So if I factor 36, we'll say 9 and 4. So that would be 3 times 3 and 2 times 2. And 28 would be 4 times 7, or 2 times 2 times 7. So this would be 2 to the second times 7. And then this would be 2 to the second times 3 to the second. So we're looking at things in common only. And so it's nice because when you're looking for a GCF through the prime factorization method, you just look at your primes. Well, I see a 2 here, and I see a 2 over here. I see a 7 here, but not a 7 over here. So I know that that wouldn't be a factor. I see 3 to the second here, but not over here. So that won't be a factor. So I do see 2 to the second and 2 to the second. So that's when you go ahead and compute. Well, 2 to the second is 4. So they both have a 4 in common. So the GCF of 28 and 36 would be 4. This is a very consistent method to find your GCF. You certainly could list these out and then look for what they have in common, which would be and sometimes a little tedious. 28, you can just think of, you could list them out. You could say 1 and 28 and 2 and 14 and 4 and 7. And then you you should end with those. 36 would say 1 and 36 and 2 and 18 and 4 and 9. And what am I missing? 12 and 3. So 1 doesn't count because they all have 1 in common. I don't see 28 in common. I do see 2. They do have a 2 in common. I don't see 14. I do see a 4 in common. I don't see a 7. So 4 is actually the greatest that they would have. So that listing them is one method. But using the prime factorizations, you'll see, is an easier method than thinking about all. You still are thinking about the factors. It's just whether you want to list them out or use the prime factorization. because I'm going to encourage the prime factorization for your least common multiple as well, is what we're about to look at. So one more time, just to recap, when you're looking for your greatest common factor using the prime factorization method, go ahead and factor down to your product of primes, and then you're looking at both sets and what do they have in common. So let's look at the lowest common multiple. So we'll say 12 and 15. Now we certainly can list these out. We could skip count by 12s and we could skip count by 15s and find your list. That's a perfectly good method. 12, I'm going to use the use of exponents. And notice I put here group the bases and exponents, but we're going to manipulate the factors to make them the same. We're going to actually build these up. So here's 2 times 6 and 2 times 3. So I actually have 2 to the second times 3. 15, I have 3 times 5, and they're both prime. So I have 3 and 5. So what I mean by build up, we're just going to figure out, well, what does each side need that the other has? Well, this one's 2 to the second. This doesn't have a 2 as a factor at all, but we're going to build that up, and we're going to give this 2 to the second. This one has a 3 as a factor. This one has a 3 as a factor. 15 has a factor of 5. 12 does not. So we're going to increase that so that they are both the same. And then we're just going to find the product. So this is 4. 2 squared is 4. And 4 times 3 is 12. And 12 times 5 is 60. So that just means that the lowest common multiple of 12 and 15 would be 60. All right, let's look at another one. How about 45 and 60? Well, 45 would be, let's look at maybe a different type. Let's say 3 and 15. 3 is prime. And 15 is going to have 3 and 5, so we're going to say 3 squared and 5. 60, I notice, ends in 0, so 10 would be a good starting point. 10 would be 2 times 5. 6 would be 2 times 3. They're all down to prime, so we would say 2 to the second times 3 times 5. And we're looking at for our LCM. So again, we're trying to build up. This one has a 2 to the second. This one does not. So I'm going to put build up with 2 to the second. This one has 3 to the second. This one only has 3, so we're going to make that 3 to the second. And this has 5, and this has 5. So let's see, we've got 4 times 9 times 5. So 4 and 5, that's 20 times 9. That should be 180. So the least common multiple of 45 and 60 would be 180, and we did that by using the build-up method. So that's all for this video. I'm going to upload and start another video that will begin with integers and absolute value, but this is all for the discussion of number theory with greatest common factor, least common multiple, divisibility rules, and other ideas with factors.